Okay, let's unpack this. Imagine you're diving into the essential building blocks of our world. Maybe you're gearing up for that big inorganic chemistry exam,
Yeah.
or just really curious about the elements that literally make us. Today, we're taking a deep dive into Group 16 of the periodic table, a crucial chapter from Shriver and Atkins Inorganic Chemistry, 5th edition. This group is, well, it's packed with elements vital to our existence, yet full of surprising twists and turns.
Precisely. Think of our deep dive today as sort of a detective story into Group 16. We'll be uncovering clues about elements like oxygen and sulfur, piecing together how their unique personalities allowed life to flourish, shaped our planet, and, continue to surprise us with their unexpected chemistry.
Yeah.
Right down to the radioactive mysteries of polonium. Our mission is to extract the most important nuggets of knowledge from this material, ensuring you walk away well-informed and with some truly aha moments.
Yes.
All explained step by step as if you have the textbook right in front of you, but without needing to see a single diagram.
Yeah, that's right. This is your shortcut to understanding the chalcogens, a name that even has a cool historical tie to copper, apparently referring to their association with bronze.
Interesting.
We'll explore their unique characteristics, their essential roles, and some truly unexpected chemistry, making sure you grasp the core concepts, visualize the structures, and see how it connects. The essentials, getting to know the group. So who are these chalcogens? It's oxygen, sulfur, selenium, tellurium, and polonium. And right off the bat, as you journey through the chapter, one element truly stands out as, well, quite different from the rest.
Here's a crucial insight right away. Oxygen, the star of this group, is really a complete outlier. It's at the very top of Group 16, and its unique position profoundly reshapes, the entire group's characteristics.
How so?
Think about it. Oxygen is a gas. It's the second most electronegative element, has a tiny atomic radius, and critically, it lacks those accessible orbitals that its heavier relatives possess. These factors profoundly influence its chemistry, limiting its coordination number, that is, how many atoms it can directly bond to, typically to no more than 3 in simple molecular compounds.
Ah, I see.
This is a stark contrast to its chemical relatives, its congeners, like sulfur, which frequently reach coordination numbers of 5 and even 6, like in sulfur hexafluoride SF6.
Right, SF6.
Understanding why oxygen is so different is really key to understanding the chalcogens as a whole.
And it's truly remarkable how pervasive oxygen is. I mean, I was astonished to learn it makes up a staggering 46% of Earth's crust by mass, 86% of the oceans.
Yeah, huge amounts.
And 2/3 of you and me by mass. But what's even more fascinating from a historical perspective is that early oxygen on Earth was actually toxic to many species, wasn't it?
Indeed, this raises an important question. How did life adapt? The oxygenation of the atmosphere, largely driven by oxygen evolving photosynthesis over, well, billions of years, caused a dramatic shift.
From anaerobic to oxygenic.
Exactly. From oxygen-free to oxygen-rich conditions, this had a profound effect on water chemistry. For instance, sulfur, which was largely present as sulfide in anaerobic waters, got oxidized to sulfate.
Okay.
Metal ion concentrations also changed dramatically. In the ancient oceans, iron was present as Fe, which is soluble, but on oxygenation, Fe oxidized to Fe,
Which isn't soluble.
right, leading to the precipitation of iron hydroxides and oxides. Those massive banded iron formations we see today in places like Canada and Australia with magnetite and hematite,
Yeah.
they're testimony to this precipitation from the oceans like 2 to 3 billion years ago.
Wow. That's a critical piece of Earth's history. Now contrast that with sulfur. While oxygen's single OO bond enthalpy is relatively weak, 146 kilojoule, making peroxides powerful oxidizing agents,
Right.
sulfur's SS bond enthalpy is much higher at 265 kilojoule. That's remarkably strong.
It really is. Exceeded only by carbon and hydrogen bonds, this strength allows sulfur atoms to catenate.
Catenate, meaning they form long chains and rings with themselves.
Exactly. If oxygen could do that, well, imagine what our atmosphere would look like.
Oh, yeah.
Instead, sulfur's catenation leads to a huge number of allotropes and polymorphs more than any other element. All the crystalline forms of sulfur you can isolate at room temperature consist of these distinct SN rings.
Like the S8 ring.
Yes, the most common is that 8-membered crown-like ring.
Okay.
And this ability of sulfur to catenate is crucial for understanding its biological role, as SS linkages, written as RSSR, are vital for stabilizing protein structures.
Those disulfide bridges.
Precisely. They form permanent connections between cysteine residues on different protein strands or different parts of one strand. Very important.
And as we move down the group, we encounter selenium, tellurium, and then polonium. Polonium sounds particularly intriguing. All radioactive isotopes.
That's right. All 29 of its known isotopes are radioactive, making it intensely toxic, something like 2.5 by 1011 times as toxic as hydrocyanic acid.
Whoa.
Yeah, it's been found as a contaminant in tobacco and naturally in uranium ores.
So if we connect this to the bigger picture, there's a clear trend in this P block group.
You see it clearly. Metallic character generally increases as you go down the group. Oxygen, sulfur, and selenium are nonmetals.
Right.
Tellurium is a metalloid sort of in between, and polonium is definitely a metal.
Okay.
And all members other than oxygen are solids under normal conditions, and they all occur in several allotropic forms, again showcasing that structural diversity we saw with sulfur. 2. Simple compounds and unexpected structures.
Okay, we've covered the general characteristics. Now let's talk about simple compounds, maybe starting with hydrides. The most important, of course, is water. What makes it so utterly unique compared to its heavier group 16 relatives?
Water, H2O, is truly unique among these hydrides. Its melting point, 0 degrees C, and boiling point, 100 degrees C, are significantly higher than for compounds of similar molecular mass or its heavier cousins like H2S.
Like H2S, which boils way down at negative 60.3 degrees C.
Exactly. This huge difference is down to extensive hydrogen bonding between hydrogen and the highly electronegative oxygen. You often see it written as HOHO, that dotted line showing the strong intermolecular pull.
Right, the hydrogen bond.
And hydrogen peroxide, H2O2, is also a liquid, with a liquid range from 0 degrees C all the way up to 150 degrees C for the same reason, that extensive hydrogen bonding.
Okay.
But in stark contrast, H2S, H2SE, and H2TT are all toxic, foul-smelling gases. They have significantly less hydrogen bonding.
Just shows the impact of electronegativity inside.
Immense impact on intermolecular forces, yeah.
That makes a lot of sense, highlighting water's fundamental role. So we've covered hydrides, water's unique role, but these elements also form crucial oxides. Sulfur in particular gives us some incredibly important ones, right?
Absolutely. We have sulfur dioxide, SO2. In the gas phase, it's an angular molecule. You can picture a bent structure like a V with sulfur at the bottom point and oxygens at the ends.
Got it.
It's a poisonous gas, sharp, choking odor, used extensively in sulfuric acid manufacture as a bleach, disinfectant, food preservative. Lots of uses.
And SO3.
Then there's sulfur trioxide, SO3. That's a trigonal planar molecule in the gas phase. Think flat triangle, sulfur in the middle.
Okay.
But here's where it gets interesting. In the solid state, it actually forms cyclic trimers. Basically, 3 of these flat SO3 units link up into a ring.
A trimer ring.
Yes, makes it extremely corrosive. Industrially, it's converted straight into sulfuric acid without being isolated directly.
Right. It's not just the simple binary compounds where these elements shine, though. When we look beyond, sulfur, selenium, and tellurium show this amazing capacity to self-assemble into complex rings and clusters.
Oh, definitely. A whole hidden world of polyatomic structures, often as ions.
Yeah.
Indeed. Sulfur, for instance, forms many polythionic acids, H2SNO6, with up to 6 sulfur atoms chained together. Examples include the tetrathionate S4O62 and pentathionate S5O62 ions. You've got that central chain of sulfur atoms capped by oxygen groups.
You can't chains.
Then there are polyanions, like the polysulfides, SN2, where N can range from 2 to 6. The S32 ion, for example, is an angular structure like SO2.
And selenium and tellurium do this too.
Polyselenides and polytellurides also form intricate molecular architectures, sometimes described as cages or rings within rings, like the fascinating bicyclic T72 ion or the complex C112 ion.
C112.
Wow, it has a central selenium atom sitting in the middle of 2 6-membered rings, all arranged in a kind of square planar fashion.
That sounds complex to visualize.
It is. Many of these polyatomic cations, positively charged clusters of sulfur, selenium, and tellurium, can actually be produced by oxidation in strongly acidic media. Shows their versatility in unusual bonding situations.
And speaking of surprising structures, sulfur-nitrogen compounds. I heard some have truly wild properties.
Here's where it gets really interesting. A genuine aha moment that, challenges conventional understanding. Cyclic tetrasulfur tetranitride, S4N4. It's a pale yellow-orange molecule made by passing ammonia through SCl2. It has this distinctive cradle-like 8-membered ring structure.
Cradle-like.
Yeah, imagine the 4 nitrogen atoms lying flat in a plane, and they're bridged by sulfur atoms that stick up above and down below that plane.
Oh.
It's endergonic, meaning it actually stores energy rather than releasing it when it forms,
Yeah.
which is why it can decompose explosively if you initiate it.
Right, unstable.
But even more remarkable is disulfur dinitride, S²n². This is formed by passing S4n4 vapor over hot silver wool.
Okay.
Despite being even less stable than S4n4, it explodes above room temperature. It can polymerize at 0 degrees C over several days to form SNN.
That's a polymer.
A polymer. This bronze-colored zigzag chain polymer, SNN, is the first known example of a superconductor that doesn't contain any metal constituents.
Wait, a non-metallic superconductor?
Exactly, active below 0.3 Kelvin. This isn't just some quirky compound, it offers a profound insight. A non-metallic superconductor.
That completely defies what you'd expect.
It does. It reveals how structure can unlock properties we typically only associate with metals. It fundamentally expands what we thought was possible in material science. 3, diving deeper into specific elements and their chemistry.
That's a truly mind-bending discovery. Let's zoom back in on oxygen for a moment. We hinted earlier at O2's unique electronic setup. Can we unpack why its electronic structure is so special, beyond just being crucial for life?
Right. Dioxygen O2 is crucial, yes, but here's a subtle yet powerful detail about its electronic structure. Its molecular orbital description is unique because the outermost 2 electrons occupy different antibonding pi orbitals, and they have parallel spins.
Parallel spins, so it's paramagnetic.
Exactly, meaning it's attracted to a magnetic field. This gives it a ground state we call 3 triplet sigma G minus.
Okay.
However, there are also higher energy singlet states. For example, the 1 singlet delta G state, which lies just slightly above the ground state. It's particularly interesting because its electrons are paired up in 1 pi star orbital, leaving another empty.
So it's different from the ground state.
Very different. Think of it as a temporarily excited, more aggressive form of oxygen. This allows it to react as an electrophile, an electron pair acceptor. For instance, it can add across a diene, sort of mimicking a Diels-Alder reaction. This singlet oxygen is even implicated as one of the biologically hazardous products of photochemical smog.
So if this singlet oxygen is so reactive, why are many of oxygen's reactions at its ground state, say with organic compounds, surprisingly sluggish, even if they look favorable thermodynamically? Is it just activation energy?
That's a crucial point about activation energy, yeah. Several factors contribute to this sluggishness. First, with weak reducing agents, a single electron transfer to ground state O2 is actually mildly unfavorable thermodynamically.
Okay.
Second, the ground state of O2, with both those orbitals singly occupied, isn't an effective Lewis acid or base, so it has little tendency to undergo common displacement reactions.
Right.
And finally, yes, the high O2 bond energy, 497 kilojmol, means there's a high activation energy for reactions that need the molecule to break apart first.
Makes sense.
Metallenzymes are really remarkable because they manage to catalyze the 4-electron reduction of O2 to water in biological systems, effectively bypassing these activation barriers.
Providing specific pathways.
Exactly, making life as we know it possible.
Okay, moving back to sulfur. We talked about its many allotropes and that strong SS bond. How do we even get it out of the ground? And what are some of its other uses besides making sulfuric acid?
Sulfur can be extracted from underground deposits using the Frasch process. That involves superheated water, steam, and compressed air to basically force the molten sulfur up to the surface.
Like pumping it out?
Kinda, yeah. Increasingly, though, the Claus process is used. That extracts it from H2S found in natural gas and crude oil.
How does that work?
H2S is first partially oxidized to SO2, and then that SO2 reacts with the remaining H2S to yield elemental sulfur.
Okay.
The common yellow form of sulfur is orthorhombic IS8, made of those crown-like S8 rings, and all other forms eventually revert back to this stable version. But if you heat molten sulfur above about 160 degrees C, those rings actually break open and polymerize into helical Seth-N chains.
Like the SNN polymer.
Sort of, but just sulfur this time. It forms a metastable rubber-like material that you can actually draw out from the melt and quench. Pretty versatile stuff.
And uses beyond sulfuric acid.
Oh yeah. Gunpowder, vulcanization of rubber making tires durable, and of course, yes, extensively in sulfuric acid manufacture.
And let's not forget the sulfur cycle. Box 16.3 in the textbook illustrates it. It's absolutely essential to all life, right? Being in amino acids like cysteine and methionine.
And in many key active site structures and proteins, yes. Microorganisms play a huge, fascinating role in its transformations, constantly shifting sulfur between its different oxidation states.
Redox transformations.
Exactly. The redox extremes are sulfate, the most oxidized form, and H2S and its ions, HS2, the most reduced forms. Many classes of organisms live in ecological niches defined by these transformations, driving the global sulfur cycle.
Like what kind of organisms?
Yeah. Well, for example, sulfate-reducing bacteria like Desulfovibrio. They reduce sulfate to sulfide under anaerobic conditions, basically breathing sulfur compounds instead of oxygen.
Wow.
Conversely, you have sulfide-oxidizing thiobacilli. They use O2 to oxidize sulfide or elemental sulfur or thiosulfate all the way back up to sulfate aerobically.
And these microbial reactions can cause environmental issues.
They definitely can. Acid mine drainage is a big one. Certain thiobacilli can oxidize iron sulfide deposits like pyrite, producing highly acidic conditions, sometimes with pH values as low as 1.5.
Ouch. Very
Very damaging to ecosystems, yeah.
That's a vital distinction.
Yeah.
Now, the hydrides of group 16 are also a study in contrasts. Hydrogen peroxide, H2O2, for example. It has some powerful and sometimes dangerous properties.
Indeed. H2O2 is a very pale blue, viscous liquid, higher boiling point than water, 150 degrees C, and it's denser. It's a good oxidizing agent,
But unstable.
but thermodynamically unstable with respect to disproportionation breaking down into water and oxygen. This reaction, though slow on its own, can be explosive and catalyzed.
Catalyzed by what?
Metal surfaces, even alkali that dissolves out of glass containers. That's why hydrogen peroxide solutions are typically stored in plastic bottles with stabilizers added.
Okay.
And its relatively weak OO bond can also lead to the formation of highly reactive hydroxyl radicals. Remember the Fenton reaction with F2 plus ions?
Vaguely.
That reaction generates hydroxyl radicals. The hydroxyl radical is one of the strongest oxidizing agents known. It can have lethal consequences biologically, like damaging DNA.
So a powerful but volatile compound. But despite its dangers, it's also considered a green oxidant in many applications. That seems like a paradox.
It is a fascinating paradox. Its versatility as an oxidant, combined with its, totally innocuous byproducts, just water and oxygen, makes it incredibly valuable.
It's like bleaching.
Exactly. Bleaching paper and textiles, treating wastewater. It even minimizes odors by preventing the production of smelly H2S in sewers.
So it replaces things like chlorine bleach.
Increasingly, yes, because it's much more environmentally benign. However, you still have to handle it carefully because its decomposition can be catalyzed by so many things.
Like iron contamination.
Exactly. F3+ is a highly effective catalyst for H2O2 decomposition, so contamination by iron must be minimized when it's made and stored.
Right. And our industrial workhorse, sulfuric acid, H2SO4, much more than just a strong acid, isn't it?
It absolutely is. Sulfuric acid is a dense, viscous liquid. Yes, it's a strong Brensted acid in water for its first deprotonation, but it's also a fascinating non-aqueous solvent.
Non-aqueous. How?
Due to its extensive autoprotolysis, that means it reacts with itself.
Like water does. H2O plus H2O gives H3O plus and OH.
Precisely. Sulfuric acid does the same thing, forming H3SO4 plus and HSO4 ions, but it does it on a much, much grander scale. Its equilibrium constant for autoprotolysis is more than 110 times greater than water's.
Wow, 10 billion times greater.
Yeah. This property makes it a very effective medium for specific reactions, like preparing those polychalcogen we discussed earlier, or even generating the nitronium ion, NO2 plus SASE, which is the key species for nitration reactions in organic chemistry. Industrially, though, over 80% is used for fertilizers, and it's produced on a massive scale by the contact process.
Which involves
Catalytic oxidation of SO2 to SO3, which is then absorbed into concentrated sulfuric acid. 4. Final takeaways and a provocative thought.
Wow, what a journey through Group 16. From the unique properties of oxygen that enabled life to flourish to sulfur's incredible ability to catenate and form all those diverse structures, the intriguing chemistry of selenium and tellurium, and the, radioactive mysteries of polonium, we've certainly seen how the position of an element in the periodic table, its electron configuration, even subtle differences in bond energies can lead to such a rich tapestry of chemical behavior.
Indeed. We've seen how hydrogen bonding makes water and hydrogen peroxide liquids, while their heavier counterparts are those toxic, foul-smelling gases. We've explored the complex redox chemistry of sulfuroxyanions and the surprising inertness of compounds like SF6 that's mainly due to steric protection, the sulfurs being crowded, along with the remarkable discovery of that non-metallic superconductor, SNN. And we truly glimpsed how the evolution of Earth's atmosphere dramatically impacted the speciation, the chemical forms of elements like sulfur and iron in our oceans, leading to those huge banded iron formations.
So what does this all mean for your understanding of chemistry as you continue your studies from this chapter?
Well, it means that even within a single group of the periodic table, the chemical landscape is incredibly varied. The fundamental principles of bonding, structure, reactivity we've discussed, they underpin countless applications.
From industry to biology.
Exactly. From industrial processes like sulfuric acid production to the very biology of life, and even the development of advanced materials like that superconductor. Understanding these nuances is really key to predicting and manipulating chemical reactions and truly mastering inorganic chemistry.
And here's a thought for you to mull over. Considering how deeply entrenched the sulfur and oxygen cycles are in Earth's geology and biology, and given the extreme toxicity of polonium, what might be the long-term subtle implications of increasing human-induced alterations to these cycles, especially for the lesser-known trace elements like selenium and tellurium?
That's a good question to ponder.
That's it for this deep dive. We hope you feel much more informed and ready to tackle your next chemistry challenge. From all of us at the Deep Dive and the Last Minute Lecture team, thanks for listening.